All right. All right. Your quizzes are coming around. I didn't get a chance to look at the grade distribution on it, but from what I guess, it went pretty well. From what the graders said. Oh, well, I'll withhold comment until I look. All right. Now with transient problems, since we're doing this, you've had a second to look at them. Did you have any questions about any of the homework? Because remember, this stuff comes at you hard and fast. We're going to have a quiz this Friday. It's based on this stuff, so you got to stay ahead of it, sort of. Did you have a question? Go ahead.
I was just going to ask if we had a quiz this
Yeah,
Friday.
this Friday. Absolutely. It'll be on transient. So, I mean, this stuff is something we got a lot of material to cover. It's going to keep on coming at you. If you keep up with it, you won't have a problem. You have to keep up with it all the time before the next lecture, and then you'll be fine, usually. Any questions? Yes?
Could you do number 31?
31?
331.
Okay, 331. Thank you. I'm just trying to encourage you, by the way. I'm not trying to depress you. Just, you know, make sure you feel the challenge and meet it. Don't wait, because you get destroyed. Yeah, I'm going to tell you, you picked the tricky one. This one, the problem she picked is one that'll, if you understand the basics, you'll do well, but this one can be tricky. All right, this is the problem, and they want just VC of T. So the only thing they care about is this voltage across the capacitor. And they have two switches that both act at T equals 0 to close. You all with me? So what I'm going to do, since there's really two states for this circuit, before is T equals 0 and less, and then after T equals 0, correct? I'm going to take this, I'm going to look at what this circuit looks like for T less than 0, because we need to get the voltage across the capacitor for T less than 0, don't we, class? That's the first thing I usually say you need to do. So for that, it looks like this. Now, I'm going to show the capacitors just an open circuit so you can better appreciate what really is there for T less than 0. You literally take the capacitor out. Y'all follow me? It's just an open circuit. You're looking for that voltage across that open circuit. Then you have 2K, 2K, and is it 2 milliamps, right? In the problem? So this is what the circuit looks like for t less than 0. And remember, you can use any tool in your toolbox to solve this. You don't have to use any one way. But they're ultimately after the voltage across that capacitor. I've taken the capacitor out. Y'all understand that? All right. Now to do this, here's how I would do it. You can do it any way you want. I combine things. You see you have 2K in series with 2K over there? Can you all see this 2K in series with 2K?
Yes.
Make it 4K, okay? Sure, just make it 4K ohms. All right? Things are getting easier. What else? How would you like to do it? And again, there's no right or wrong way. I'm going to suggest this. Remember the source transform stuff I showed you? Here's where it comes in handy. I've got 2K and 2 milli, right? Can't I make that 4 volts in series with 2K? How many see that right here? Y'all with me or not?
Will you repeat that one more time?
Sure. Right here, I have 2K ohms in parallel with 2 milliamps current source. Correct, class? Can't I make an equivalent of 4 volts 2K times 2 milliamps in series with 2K? How many see that? All right, so that's what I'm going to do. Is that answering your question? All right. Now, remember, that's what I want. What else can I do? At this point, I don't have to do anything else, but there's one thing I'm probably going to do. What would you like to do?
Combine those two numbers.
How about those 2Ks add up to 4K? Agreed, class? Can you all see in the back there, guys? All right, so I'm going to make these 4K. Now, if you want, and this is totally up to you, I could do another source transfer. And what? I could put 3 milliamp in parallel with 4K, right? Right, go from voltage in series to current in parallel. And then I could put what? I could put 1 milliamp in parallel with 4K. Y'all with me? Now again, you don't have to do it. You follow me on this? If I did another source transform, this would become a current in parallel with 4K. And this would be what? A current parallel with 4K as well. Do y'all see that? You want to do it that way? Okay. So it would look like this. I would have 3 milliamp going up. Then I would have 4K here, right? Here's where I want my VC. And then I would have 1 milliamp in parallel with 4K. Do you agree with this, everyone? I'm just doing it. Yes, sir.
Could you also just add the batteries on that first step of the voltage sources? Or is
Where?
that not allowed?
What you're after is, you're saying, since there's no current flowing here, right?
Yeah.
You're saying I could just do a loop and find the current, right?
Yeah.
Sure, you could do that. Here's what he's really saying. I could say, how about if I just get this current? I'm doing it that way just so everybody appreciates that. This is probably the easier ways over there. But if we wanted to go this way, we could say, I want that current. So I'm going to assume clockwise, and I would have 12 volts here, minus 4K minus 4K minus 8K times I, right? And then minus 4 equals 0. Isn't that what you're saying?
Yeah.
And then I would take what? That would be 9, right? I'm sorry, 8, pardon me, 8. And I would have 8 volts over here equal to 8KI, right? Because I get rid of the minus, right? And that means I equal 1 milliamp, right? That's what you're saying. And if I had I equal 1 milliamp, then I know the voltage here would be 4 volts, and this would be 4 volts, right? You can do it this way. And therefore, if you wanted the open circuit voltage here starting at the negative, increase of 4 increase 4 would be 8 volts, right?
Yeah.
Y'all hear that, class? You understand why I did that? Because he suggested it. That's one way. You can do it that way. I'm showing you source transforms just to make sure you see how they simplify things over here. Now, what do you see happening here? We're going to get the same answer. What's the 3 milliamp and 1 milliamp? What can I do with those two current sources, anyone? Add them up to 4, right? Y'all agree with that, class? Sure. I'm just going to put it 4 over there. What about the 4K in parallel with 4K? Aren't they in parallel? Let me do it that way. So what do I replace them with, class? 2K, sure. So what's the voltage across the 2K? 4 milliamps times 2K is 8 volts, right? Y'all see the voltage across this, the voltage across the capacitor, where the capacitor was. How many see that? In the back there, y'all see it, class? Sure. So you get 8 volts no matter what is the point. So VC for t less than or equal to 0 is 8 volts. Good, check that box, right? Now, the next thing, since you asked, doesn't have to be in any specific order, but we're going to find out what this circuit looks like for t greater than 0. We're going to find the voltage across that capacitor as t goes to infinity. Y'all with me? I want to make sure everybody's there. All right, and what I'm going to do is erase this. So, y'all mind if I just close the switches here? We're going to go for t greater than 0 now. So I'm going to close the switch, and that becomes a short. This is going to be for t greater than 0. This becomes a short, and I have some comments. This is what the circuit would look like for t greater than 0. Do y'all agree with that? Everybody, class? Now, what do you see happening here? Well, that's a short circuit, right? You see how all this current has to circulate around there? All right? Effectively, what it does is take this point that's shorted to ground, and it shorts it to ground. It gets rid of this resistor entirely. Do you all see that? Well, I take it back. Yeah, that switch shorts to ground, so this point becomes grounded. That resistor no longer has any effect. You all see that? If I take this point and short it to ground, then you what? You simply circumvent that resistor. And think about it, this is 0 ohms in parallel with anything is still 0 ohms, isn't it, class? With me? So effectively, this is gone. You can just say that's 0. Now, this point goes to ground, doesn't it, class? Do you all see that? Because the switch closes, these two have the same potential. If you want to put a ground there, you can. Which means this part of the circuit is gone as well. Anytime you take something shorted to ground, whatever's on the other side makes no difference. Y'all follow me? It literally isolates that portion of the circuit. Now, what is the voltage across that capacitor going to be at t going to infinity and why? Anyone?
0.
Why? You're right.
There's nothing going into it.
There's no energy source to sustain that voltage. Y'all follow me? There's no power. If there was a battery, maybe it wouldn't, right? But there's nothing left in that circuit to keep that capacitor charged. So if the capacitor can discharge, it will, and it surely can. Y'all see there's 2 resistors there? So now we know VC as t goes to infinity is 0. We're getting there. Now what's the next thing we have to do? Do you remember? We need to find the Thevenin equivalent resistance across that capacitor, as if the capacitor is the load, right? Do you all remember this, class? And somebody brought that to my attention that it is as if the capacitor is a load, right? So what is that Thevenin resistance going to be? Just think about it. What resistance is across those 2 terminals? Now, I hope you can see this by now. How many see that the 2K and 2K are in parallel? All right, by now you should see it, right? I could literally take that and bend it this way, and take this and bend it this way if it helps, but you all see that they have the same exact voltage across them. If you put a voltage here, it would be in parallel across both of those. You all see it? So if you look there, the R Thevenin would be 2K in parallel with 2K or 1K. okay? Now, after that, we calculate the decay time constant called tau, right? And tau, let me put it, Vc as a function of t is really k1 e to the minus t over tau plus k2, where tau is equal to R Thevenin times c. Now we've got R Thevenin as 1k, that's 10 to the third, and then we have 200 microfarad. That's 2 times 10 to the minus fourth, isn't it, class? 200 times 10 to the minus 6 is 2 times 10 to the minus fourth, times 10 to the third would be 2 times 10 to the minus 1, or 0.2, or 1 over 5. Either one works. Do y'all agree with that? Can you all see it in the back, guys? All right. So now, if we have that, we go back to here and we evaluate K1 and K2. Well, K2 is the given. Do you remember what K2 was? Anyone?
The 0?
Yeah, but what? You're right. K2 is really the voltage on the capacitor as t goes to infinity, right? How many see it's 0? Right? Y'all with me? So if it's 0, then don't even write it down. And if it's 0, y'all know that K1 is just the voltage of t at 0, isn't it? Right? It has to be. So K1 right there is just 8 volts, isn't it, class? So that means Vc of t is just equal to 8 e to the minus t, or really 5t. And this is true for t greater than or equal to 0. That would be the voltage across the capacitor. Does that answer your question? Did you have a follow-up on that one, or?
So what is your T in the?
T is seconds, it's time, right? Time after the switch closes.
Yes.
And look at the value, as this is minus 5t or 0. It's t over 0.2, right? So if you look at this, as t goes to infinity, you get e to the minus infinity, which is really what, 0, isn't it? Y'all with me? It will go to 0. How many see this right here? Okay? All right, another question. You picked a difficult problem, by the way. Because the switches are the key thing. When the switches close, remember, it shorts out anything. It takes it to ground, so it literally isolates parts of the circuit. Go ahead.
On 326, so when you go and you're finding voltage across the capacitor at t equals 0.
Hold on for 1 second. We're way ahead now. Okay, yeah.
Yeah, we can just do the problem.
You want to do the problem?
Yeah, we can just do it, and then when I get to the part of the
Sure.
switch on, I'll ask you.
All right, and these are all very good problems. You know why? Because they show all the possible scenarios. Now, Doc, in the other book that you have for this class, there's a very limited view of the problems. There's not many. And by the time, if I give you some of these problems and I don't, and we use just the other problems, you're going to be shell-shocked. It's like, huh? How? You didn't talk about it. These problems I give you, they go through all sorts of possibilities. And they cause you to think about things in ways maybe you haven't. So come test time or quiz time, you'll be ready. All right. So for this one, we have this scenario. They're looking for the current through that 6K resistor. That's the absolute last thing you find. Huh? I'm saying this again, you ignore that. Don't look online for possible ways to write differential equations and solve that. The only thing you care about is the voltage across this capacitor. Now just think about that. We get this voltage, if I want that current, do you all see that resistor's in parallel with this capacitor? Can you all see that? So if we have this voltage, to get that current, you just divide it by 6K. You all see that? Remember, this is what you're after, not that, in a sense. This is the first thing you get. Y'all good on that? Remember, any RC problem, the thing you go for is the voltage as a function of time across the capacitor. Okay? Now this is your question. Yeah.
Wait, so no, that's what my question was. Can you re-explain that? So how do you get 24 volts for that voltage?
We didn't get any voltage yet.
Okay.
You're way ahead of me. We just wrote the problem up there, right?
Okay, I thought you were just saying that.
Now, if you knew the voltage, then you would take that voltage and divide it by the resistance to get the current through that resistor. That was my point. You okay with that? All right. Now, work with me on this one. And force yourself to think critically about it. All right, what are the steps? For t less than 0, all right, I look at what the circuit looks like. Now listen, just listen, don't think. This looks like an open circuit, right? So I'm not even going to put the capacitor in there. I'm going to go ahead and put that current source. That's 4 milliamps, right? Then I got 3K there. And I got this deal going on. And then I have 6K. I bet you see this now. Y'all agree with that? I want you to everybody take a careful look and convince yourself. Make sure you see it. How many see that that's it? For t greater than 0, or less than 0, right? Nothing's changing. That switch is open, so I don't even draw it. This is what the circuit should look like, right? And that's an open circuit for that capacitor on purpose, so you don't even think that anything can flow there. That's the reason I'm drawing it that way. So how do I get this voltage? Now, just think about it for a second, logically. It's over here, right? How do I get that voltage? All of that current must flow around, right? What's the voltage on this 6K then? 4 milliamps times 6K is 24 volts. Is that class? How many see this? So this is 24 volts. How many see that 24 volts is exactly VC? It's exactly across these 2 points, isn't it, class? Y'all see it? In the back there too, guys? Can y'all see it? It's very obvious. The current is in series with everything, right? These 2 points, nothing flows here, right? So across these 2 points, just go from the negative and increase 24 volts. You see it? So here I have VC for t less than 0. 24 volts. You were ahead of me. That's what you were asking about, right?
Yes, that's what I was asking. I think I'm confused because I'm not understanding why we ignore the 3K resistor. Why do we choose?
What are we after? We're after the voltage across here, right?
Yes. So
Could we go this way to get the voltage? We would have to go from here to here, right?
Right.
Why can't we go that way, anyone?
Because you can't go across the voltage.
We don't know the voltage
current.
across that current source. You can't sum voltages through a current source. But we know this voltage, so if I start at the negative and go here, it's an increase of 24 volts at this point. Y'all with me? Yeah.
Yes.
Could you get voltage, or could you, I probably didn't want to advise it, but could you get the voltage from that current source by just doing replacement with?
Well, okay. Here's what he said. He said, what if we do a source transfer? Yeah, if you want to, yeah, you could do it that way, but what do you find? You get, what, 12 volts, right? In series with 3K, it's going to end up with the same result. You don't even need to fuss with that. Don't make more work for yourself. I'll give you plenty. And people do make problems much more difficult. They find ways, and they don't mean to, they just don't think before they act. I promise you, I'm trying to warn you, think before you act in this case. All right, that's that. Now for t greater than 0, I want you to listen to me on this one. This is showing a lot of information. When t is greater than 0, this switch closes, right? Everybody see this? When that switch closes, it gets rid of it. Everything on that side is effectively not there. This becomes ground. Do you all see that, class? How many see that? All right, so I'm going to just do it. Now, it doesn't matter the order we go to the next step, but I need to find the voltage across that capacitor as t goes to infinity. By the way, at infinity, if there was a source there, then the capacitor would look like an open circuit again, because nothing would be changing with time. You follow me? But here, we can say what the voltage is across that capacitor as t goes to infinity because of a simple fact. Are there any sources there? Any voltage or current sources left? Where does the voltage going to go to, class? It's going to 0. You all see that? Sure. So that means voltage across the capacitor as t goes to infinity is 0.
Can
Oh.
you draw it out like
I'm
with
sorry?
the ground?
What, say again?
Could you draw it with the ground, just so I can place? Because you just use that same thing.
You can put it that way, right? I mean, you can put a ground in any time. It's just a reference point for every measurement. It doesn't have to be there, you can put it in. You with me, class? All right. Now, what's the next thing I do? Anyway. R Thevenin. What's R Thevenin going to be and why? It's what? The Thevenin equivalent resistance across those two terminals, right? So if I took, sometimes this helps people. If you want to know what's across those two terminals, just take a black marker to the top, take a different color on the bottom, and if those encompass everything that's left, anything that's got black and purple on either side is in parallel. You all see that? That's a simple way of figuring out what's in parallel. How many see this right here? You all see they're in parallel. What is it going to be? 6 in parallel with 3 is 2K, right? You can multiply them. I think when I was in high school, they used to do this. If you want to know parallel values, take the first resistance times the second over the first plus the second. It's the same thing as 1 over R1 plus 1 over. And you would get 6 times 3, right? Over 6 plus 3, or 18 over 9, which is 2. Right? 2K. All right, next is tau. What is tau? That's 1.5 times 10 to the minus 4th times 2 times 10 to the 3rd is what? Did you say 3 times 10 to the minus 1 or 0.3? Who said it? You're right. Isn't it? What's 150? 150 is really 1.5 or 3 halves times 10 to the minus 4th times 2 times 10 to the 3rd, or it's simply what? 3 times 10 to the minus 1, or 0.3. Isn't it, class? You agree with that? All right, so now I've got tau. What's my final step?
Can you go through a little bit more on the math solving for tau?
It's R Thevenin times C, isn't it? Who asked that?
I did.
You follow me on that?
Yeah.
All right, R Thevenin is 2K. C is 150 microfarads, right?
Yeah.
All right, so that would be 2,000, right, times 150 times 10 to the minus 6, right? If you want to write the whole thing out.
Okay.
All right, you with me?
Yeah, that helps.
That's all it is. R Thevenin times C is tau. Correct, class? All right, what's my last step? Then I come over here and I say VC is a function of t is K1 e to the minus t over tau plus K2. What can you tell me about K2 and why? Why is it 0? Voltage is 0, right? We've proved that. K2 must be 0. Do you agree, class? If it wasn't 0, then the voltage wouldn't go to 0, right? We'd have lied. Yeah, it goes to 0. So K2 is gone. How about K1? How do we get it? At this point, it's by inspection just left. It's got to be 24, doesn't it, class? Because that's the voltage at t equals 0, isn't it? When t equals 0, e to the 0 is 1. It's got to be 24. Agree, class? So that means Vc of t is equal to 24 e to the minus t over 0.3. Okay? Now that's the voltage across the capacitor, but the problem asks for what? Asks for this current. So how do we get that current? We say I naught of t is simply Vc of t divided by 6k, or it's 24 over 6k e to the minus t over 0.3, or that's going to be 4 milliamps e to the minus t over 0.3 for t greater than 0. And that should be the right answer in the book. Okay, these are good problems, and they really do stretch you a little, right? All right, what's the next problem before? I wanted to work problems today. Hopefully you had a good time, or you had time to do some of these problems, because if you haven't, you're really going to be, the next batch is more fun than ever. All right, which one? Did you have one? Anybody? Yeah.
We do 3.33.
Yeah, and by the way, you'll notice one thing about these. All these problems have the voltage as t goes to infinity go to 0, right? That won't be the case. Now that I said that, maybe, I'll be happy to do that one. Let me just see if it's got a, I like that one. This one has a voltage not equal to 0, t goes to infinity. So this is a good problem. It's just what I need. Okay. And they actually want this current, right? For t greater than 0. But that's the problem. If you take a look, give me one sec. Okay, for this problem, now if you want to put a ground, you can. It doesn't matter, okay? Remember what I've told you, the only thing, this stuff, you don't worry about. You worry about this. You want the voltage across the capacitor as a function of time for t greater than 0. That's your goal. Anything else is secondary. You get that. You got everything. So, first we have to find the voltage across the capacitor for t less than 0, right? Less than or equal to 0, correct, class? This is so important. When you do that, what happens? Well, I'll leave that as an open circuit. And how you do this is where you go to your toolbox, use what you will to solve these. You're going to need, this is the whole basis for the chapter we did on circuit analysis. You're going to need all that stuff. You can use any method you feel free to use. So, but you'll learn that some methods are better than others. These are simple problems, but it gets a lot more complicated later. So here we have 36 volts. Then you have, this is going to be for t less than or equal to 0. Then you got 2K here, right? Then here's the capacitor, and I on purpose make it an open circuit. Right there. Here's 6K. And then you have 4K. And then you have 12 volts. Y'all agree with that, class? Right? I just redrew it, right, with eliminating the capacitor, and since the switch was open, I didn't even bother drawing it. Do y'all see this, class? In the back there. Can you guys see it? All right, now I want this voltage. How you do it at this point is up to you. I would make one suggestion. This right here looks like a single resistor to me. You agree with that? So I'm just going to combine the 6 and 4 and make it 10K. Now, you may want to just get the current, and we can do it, well, why don't we do it that way for simplicity? I won't do source transforms. I want to get this current, none can flow in the center, right, because it's an open circuit, correct? And if I want to get that current, y'all follow me that this current is just going to flow clockwise, right? Can y'all follow me? Now if I just want this current, some of you can see it already. Can't I even combine these two resistances? Right? Sure, they're in series, aren't they? We only want that current, so it could be just 12K. What about these sources? 36 volts is trying to push current clockwise, but it's opposed by 12, so it'd be a net 24 volts pushing it clockwise. Do y'all follow me? And if you don't, I'll write it down right here. If I start at this point, I get plus 36. Then I have minus 2K times the unknown I, minus 10K times the unknown I, and then minus 12 equals 0, wouldn't I? If I just go around that loop? Make sure you can see it in the back, guys. With me? I'm just showing you, well, you can see that the 36 minus 12 is 24. And the 2K and 10K is 12K, so it's minus 12K, right? Times I equals 0. Do you agree? So here I is what? 2 milliamps, right? 2 milliamps. So I would be 2 milliamps. Now once I have that, he suggested this last time, you just get the current. Maybe you are right. Maybe it is easier. But if I have that as 2 milliamps, right? Don't I know the voltage here? Isn't that 20 volts, class? 2 milliamps times 10K would be 20 volts. Do you agree? Let me see that. Right? So that's 20 volts, right? What about this? 2 milliamps, 2K is 4 volts, isn't it? So this is plus to minus 4 volts. Now, I need to get the voltage between the negative and positive terminals. The way I've mentioned over and over, start the negative and work back to the positive. You can go that way or you can go this way. You all see that? How many see it's 32 volts? Prove it to yourself. You see it? In the back there, right? Start the negative, increase to 12, increase to 20, 32, correct? Go this way, increase to 36, loss of 4, 32. Correct, class? Y'all see this? Right? Okay. So we know this is 32 volts. Here's where this differs from the last problem. Now, hope you all brought umbrellas. That is rain, I hope, I think. So now I'm gonna go here, I'm gonna go for t greater than 0. I want you to watch this, make sure you do. So now when I take t greater than 0, you poor girls, if you just did your hair. I'm so glad there's not a function after this big one. Because I have literally seen people just about in tears because they have a problem. All right, now if you look over here, remember this is going to be for t greater than 0, right? Now listen, the switch does its thing. Please listen, y'all with me? When the switch closes, you see how it completely gets rid of all that. Everybody? Y'all see it? When the switch closes, it looks like this. This is equivalent to this electrically, so I just erase it. That's the way I prefer. Does that make sense, everybody? Don't leave more stuff there than you need. I get rid of that. It looks like this, doesn't it? Correct? Now please be attentive. I'm going to take a look at this circuit as t goes to infinity. Well, as t goes to infinity, there's something very important you have to understand. And you don't write this down, just listen. When I have a capacitor, the voltage across the capacitor is, and with respect to the current, Vc of t causes an Ic of t related by C times Vc of t dt is equal to I of t. Now, listen. If there is nothing changing with time, do you see the current 0? Right? As t goes to infinity, everything settles to a steady state value of V. Y'all follow me in that class? Nothing is changing with time. It means the current's 0. If the current is 0, it looks like an open circuit. That's my real point with these capacitors. When nothing's changing with time, for t less than 0, then on forever, it looks like an open circuit. As t goes to infinity, it looks like an open circuit too. So it looks like this. As t goes to infinity. All right, what's the voltage across that as t goes to infinity? Just take a look at that. How many see that you have 2 resistors in series that current can flow through? Y'all see that? Current can flow this way, right? Can flow that. It can't flow through the center because it looks like an open circuit. Do y'all agree with that? Let me see a show of hands here if you agree with that. Now, can you all see that the voltage across that is really the voltage across that 6K, isn't it? If I was to redraw that, it would look like this. This is what it would look like, wouldn't it? That's just a circuit redraw, isn't it, class? It's very obvious too, right? The only thing I did is take this and bend it straight down here because I can put that anywhere, that resistor. And I just took this one and straightened it up, didn't I? Now, what is this voltage though? V across the 6K would be what? 36, right? The source voltage, these two are in series, over 6 over 6 plus 2, or 6 over 8, right? Or 3/4 of 36. Do y'all see that, class? So it's going to be what? 36 what's that going to be? 27 volts, right? That's exactly it. So now Vc, as t goes to infinity, is equal to 27 volts, right? Y'all follow me? It's not 0 for this one. That's important. There's a source left in there, right? I'm glad you asked this. This is exactly what I wanted. All right, now, back to this thing, all right? This is what the circuit looks like for t greater than 0, correct, over here? What's the next thing I need? R Thevenin, right? So, what's R Thevenin going to be? All right, R Thevenin is across these 2 points, right? What do we have to do to that source, class? Say again? What do we do when we want the Thevenin equivalent resistance between 2 points if there is a source? Yeah.
You short the voltage source.
Yeah, short the voltage, open the current. Y'all remember that? Current sources become open circuits, right? Voltage sources become short. Y'all remember that? So if that's a short circuit, I'm going to short it right here because I'm about out of time. Now, what is R Thevenin? Can you see it? Tell me about those 2 resistors. Are they in series or parallel? How many see they're in parallel? I'm so glad I heard you say that. All right, so I got 2K in parallel with 6K, or what? 12 over 8K, correct? Or 6 over 4, or y'all follow me on that? It's what?
3 over 2.
I have this is going to be what? I'm just going to leave it as 2K in parallel with 6K so everybody can see what I'm doing. All right? That's it. And that means tau is what? R Thevenin times C. Just let me finish here. All right? Now, I'm about out of time, but y'all follow me what I'm getting. I'm going to get R Thevenin, then I'm going to get tau. Now, once I do this, I know the voltage across the capacitor will be some K1 that I don't know this time, times e to the minus t over tau. I do know tau, but I don't want to put it in yet, plus K2. Remember, K2 is the voltage at t equal infinity, right? What was that voltage? 27. Do y'all see that, class? So it's this plus 27. Now that's the voltage across the capacitor for all time greater than 0. How do I get K1? Any takers? Say again? I'm sorry?
Plug in K2 and then when t is equal to 0.
Exactly. Did you hear her? Evaluate that equation at t equals 0 and set it equal to the voltage across the capacitor at t less than 0, because they can't change instantaneously. So you set it equal to 32. So then you would have 32 would be VC for t equal to 0 positive. 32 is equal to K1 e to the 0, which is 1, plus 27, right? Or K1 is equal to 5, isn't it, class? So now we have K1. Thank you, by the way. You're right. Now, once we have that, we actually wanted that current. How do we get that current I out of t? We have VC for t greater than 0, don't we, class? So how do we get I? Anyone? Just divide by that resistor. How many see that? That's a good problem. Once you let that sink in, then you won't be scared of these problems. Because, and I would recommend one thing, you do a bunch of them. Go through them. If you don't understand something, let me know where your friends know. Are you able to access the stuff on the internet? I mean, I guess on YouTube, and do you have a group or is it a Facebook page? I don't know. What do you have for us? Is it a group meet?
I think so, yeah. Yeah, it's a great.
All right, are you, anybody accessing that or not? I would recommend you do it. You know why? The students networking together usually, it's usually a real benefit for everybody. Usually if one person has a question, a lot of people have a question, and a lot of people can answer. Yes, sir? Yeah, it's on transient.